What if I told you that 2026 isn't just another year on the calendar? What if I told you it's the year when science fiction starts becoming science fact? Picture this: humans circling the moon for the first time in over 50 years. Synthetic human genomes being completed in laboratories. Quantum computers breaking the 10,000 qubit barrier. Robot hands that move exactly like yours. And a particle collider so powerful it could rewrite our understanding of reality itself. This isn't some distant future we're talking about. This is 2026. This is next year. And by the time this year ends, the world won't look quite the same as it does right now. I'm talking about the year everything changes. Let's dive in. Return to the moon. Let's start with something humanity hasn't done since 1972. Going back to the moon. For over half a century, we've been stuck in low Earth orbit. Sure, we built the International Space Station. Sure, we sent robots to Mars. But actual humans? We haven't left Earth's immediate neighborhood since the Apollo program ended. That changes in 2026. NASA's Artemis. 2 mission launches 4 astronauts on a journey that will take them farther from Earth than any human has traveled in over 50 years. But here's what makes this different from Apollo. This isn't just a quick trip around the moon and back. This is the beginning of something much bigger. The Orion spacecraft, powered by the most advanced life support systems ever created, will carry its crew on a 10-day mission. They'll loop around the moon, coming within 6,400 miles of its surface, close enough to see the craters in stunning detail, close enough to feel the pull of another world. And here's a historic moment within a historic moment. One of those 4 astronauts will be Canadian. The first person from Canada to ever leave low Earth orbit. The first to see the moon up close. The first to experience that profound moment of looking back at Earth from deep space. But Artemis II isn't the destination. It's the test run. Because the real goal? That comes later in the decade with Artemis III. That's when humans, including the first woman, will actually walk on the lunar surface again. Specifically, the moon's south polar region, where water ice hides in permanently shadowed craters. Water that could become drinking water, breathable oxygen, even rocket fuel for missions to Mars. This is NASA laying the groundwork for something permanent. Not just flags and footprints this time. We're talking about sustained human presence, moon bases, mining operations, stepping stones to Mars. 2026 is when that future stops being science fiction and starts becoming engineering reality. The Orion spacecraft will spend 2 days in high Earth orbit first, testing every system, making sure everything works perfectly. Then comes the big moment, the translunar injection burn, the moment when the main engine fires and sends the crew hurtling toward the moon at 25,000 miles per hour. For 3 days, Earth will shrink behind them. The moon will grow larger ahead of them. And then, that moment. That profound, life-changing moment when they swing around the far side and see something no human has seen with their own eyes in over 50 years. Earthrise, our blue marble hanging in the infinite black. They'll spend hours circling, conducting experiments, taking measurements, preparing for future missions. And then, the journey home. Re-entry at nearly 25,000 miles per hour. Parachutes deploying, splashdown, safe return. 4 people will return to Earth having experienced something only 24 humans in all of history have experienced before them. And when they land, the whole world will know, we're going back, we're going to stay, and this time, we're going even further. Creating life from scratch. Now let's talk about something that sounds like it came straight out of a science fiction novel. Creating a human genome from scratch on a computer. In 2010, scientists created the first artificial life form, a bacterium with completely synthetic DNA. It was groundbreaking, revolutionary. but it was also simple. 473 genes, 531,000 base pairs, tiny compared to what comes next. Because in 2026, the Human Genome Project reaches completion. And this isn't about reading DNA anymore. This is about writing it, creating it, building genetic code from nothing and watching it come to life. Think about the scale of this for a moment. The human genome has 3 billion base pairs, 20,000 genes. That's orders of magnitude more complex than anything humanity has ever synthesized before. And yet, by the mid-2020s, we've figured out how to do it. But why? Why create synthetic human genomes? What's the point? Here's where it gets interesting. Once you can write genetic code, once you can design DNA sequences from scratch, you can do things that were impossible before. You can grow transplantable human organs in the lab, eliminating donor waiting lists forever. You can engineer cells that are completely immune to viruses, cancer-resistant cell lines, cells that can't be infected by HIV or influenza or any pathogen we throw at them. You can produce vaccines faster and cheaper than ever before. When a new pandemic emerges, you don't wait months for production. You design the vaccine digitally, synthesize the necessary genetic sequences, and start saving lives within weeks. This is medicine entering a completely new era. An era where we're not just treating diseases, we're rewriting the genetic code to prevent them from happening in the first place. But let's be honest about something. This technology doesn't stop at medical applications. Once you can write human genomes, once you can design genetic code with this level of precision, the ethical questions become massive. Could we design humans with enhanced intelligence, increased lifespan, immunity to radiation for space travel? Technically? In the distant future, yes. Should we? That's the question that will define the rest of the century. For now, in 2026, we're focused on cells in dishes, individual cells with synthetic genomes, proving the technology works, proving we can write the code of life itself. But the researchers working on this know exactly what they're creating. The foundation for a future where genetic engineering becomes as precise as software engineering. The ethical frameworks are being built alongside the technology. Oversight committees, international agreements, guidelines for what's acceptable and what crosses the line. Because everyone involved knows this. Once you can write genomes, once you can design life from scratch, you can't uninvent that knowledge. 2026 marks the moment when humanity gains the ability to intentionally direct its own evolution. What we do with that power will define us for generations to come. Unlocking the universe's secrets. All right, let's talk about smashing particles together at nearly the speed of light. Because in 2026, humanity fires up two of the most powerful scientific instruments ever built. First, the High Luminosity Large Hadron Collider. That's a mouthful, so let's call it the HLLHC. This is the upgraded version of the machine that discovered the Higgs boson back in 2012. But this new version, it's not just an upgrade, it's a quantum leap. The HLLHC can produce 10 times more data than the original. It can detect particles and events so rare that the previous collider would have needed decades to observe them. It can create 15 million Higgs bosons every single year. For context, the original LHC produced 1.2 million total in its first 2 years of operation. Why does this matter? Because the Higgs boson is weird. It's the particle that gives other particles mass. It's fundamental to understanding why matter exists the way it does. And the more Higgs bosons we can study, the more we understand about the deepest nature of reality. But here's what really excites physicists. The HLLHC might find something beyond the standard model. That's the current framework, explaining how particles and forces work. And while it's incredibly accurate, physicists know it's incomplete. It doesn't explain dark matter. It doesn't explain dark energy. It doesn't fully explain gravity at quantum scales. The HLLHC might be the key to unlocking those mysteries. Every collision is a chance to see something that shouldn't exist according to our current understanding. And when you're producing 10 times more collisions, your odds of discovering something revolutionary go way up. Now, running alongside this monster machine is another beast entirely. The International Linear Collider. This one's been in the works for over 25 years. 300 universities and laboratories from around the world collaborated to make it happen. Unlike the circular Large Hadron Collider, the ILC is linear. Two accelerators facing each other across 31 kilometers, 19.3 miles of high-energy physics, hurling particles and antiparticles toward each other at relativistic speeds. The collisions aren't as powerful as the LHC, but they're far more precise. Think of it like the difference between a shotgun and a sniper rifle. The LHC gives you raw power, the ILC gives you surgical precision, and that precision matters when you're hunting for things like supersymmetric particles. These are theoretical particles that should exist if certain theories about the universe are correct. We've never seen them, but if they're real, the ILC might be the machine that finally spots them. Or consider dark matter. We know it's out there. We can see its gravitational effects on galaxies and clusters. We know it makes up about 85% of all matter in the universe, but we have no idea what it actually is. The ILC could provide the first direct evidence of dark matter particles. Both of these machines represent something profound about human nature. We built devices costing billions of dollars, stretching for kilometers underground, cooled to nearly absolute zero, all to answer fundamental questions about existence. Not for profit, not for military advantage, just to know. What is the universe made of? How did it begin? What laws govern reality at its most basic level? 2026 is when we get significantly closer to answering those questions. The data these colliders produce won't just fill academic papers. It will reshape our understanding of everything. And sometimes, that pure knowledge leads to applications nobody predicted. The World Wide Web was invented at CERN, after all. Who knows what technologies might emerge from discoveries made in 2026? Russia joins the reusable rocket race. SpaceX changed spaceflight forever when they landed their first Falcon 9 booster back in 2015. Suddenly, rockets weren't disposable anymore. They could land, get refurbished, and fly again. That innovation slashed launch costs and made space more accessible than ever. But for years, SpaceX stood alone in this capability. Other companies and countries watched, studied, tried to catch up. And in 2026, Russia finally enters the game with the Amur SPG. Now let's be honest, the Amur looks a lot like the Falcon 9, those grid fins for stabilization during descent, that vertical landing capability, the plan to reuse each booster up to 100 times. Yeah, SpaceX pioneered all of that. But in the world of aerospace, if something works, you copy it and try to improve it. The Amur is smaller than the Falcon 9, 55 meters tall compared to 70 meters. It can only carry 10.5 metric tons to low Earth orbit, while the Falcon can haul nearly 23 metric tons. But here's where it gets interesting. The Amur costs only $22 million per launch. That's less than half the price of even a used Falcon 9. Russia is essentially saying, we can't compete on payload capacity yet, but we can compete on price. And for smaller satellites, for specific orbital insertions, that matters. The boosters land on platforms in the Sea of Okhotsk, north of Japan. Heavy helicopters or rail systems bring them back to the launch site. It's not as elegant as SpaceX's drone ships, but it works. And in the launch business, working is what counts. The Amur SPG is just the beginning. Russia's already planning larger, more capable versions for the 20s, full reusability for both stages, greater payload capacity, more competitive with SpaceX's evolving Starship system. This matters because competition drives innovation. When multiple countries and companies compete in space launch, costs drop, access improves, new possibilities open up. The Amur might be playing catch-up now, but every new player in the reusable rocket game pushes the entire industry forward. And as launch costs continue falling throughout the 20s and 30s, we edge closer to a future where space isn't just for governments and billionaires, where launching satellites is routine, where space tourism isn't a novelty, where moving resources from Earth to orbit becomes economically viable. Russia's entry into reusable rocketry in 2026 is one more step toward that future. Robots learn to touch. Your hands are extraordinary. Think about it. Right now, without looking, you know exactly where your fingers are. You can pick up an egg without crushing it. You can thread a needle. You can feel the difference between silk and cotton with your eyes closed. We take this for granted because we've had these abilities our entire lives. But try programming a robot to do any of that, and you'll quickly realize just how complex human hands really are. For decades, robotics engineers have struggled with this. They could build robots that were incredibly strong, robots that were incredibly fast, but robots that could gently manipulate delicate objects, that could adjust their grip based on texture and weight, that remained frustratingly difficult. Until now. 2026 marks a turning point. This is the year when robotic hands finally match human capabilities. Not sort of, not approximately, actually match them. This breakthrough comes from multiple innovations converging simultaneously. Advances in nanotechnology allow sensors small enough to detect the tiniest pressure changes. Graphene-based actuators can convert electricity into precise, fluid motion. Artificial skin, with tactile sensors, provides feedback about texture, temperature, and pressure. Machine learning algorithms can recognize thousands of different objects and intelligently plan how to manipulate them. Put it all together, and you get something remarkable. A robotic hand that can perform surgery, that can assemble delicate electronics, that can fold laundry, pour a drink, or shake your hand with appropriate firmness. But here's what makes this really revolutionary. These hands can operate autonomously. The AI doesn't need constant human input. It sees an object, assesses its properties, and figures out the best way to handle it. All in real time, all with movements that look and feel natural. This technology emerges from labs in 2026, but its impact will be felt throughout the following decades. Human-like robots become genuinely useful in environments they previously couldn't navigate. Elder care facilities get robotic assistants that can help patients with daily tasks. Factories can automate processes that previously required human dexterity. Disaster response teams get robots that can manipulate rubble and rescue equipment. And further down the line, this is a crucial step toward true android technology. Robots that don't just look human, but move like humans, interact like humans, exist in human spaces without requiring special accommodations. The hands are just the beginning, but they're an important beginning. Because once robots can touch the world the way we do, they can finally start participating in it the way we do. Quantum leap. Most computers work with bits, ones and zeros, on and off. It's simple, reliable, and it's powered every digital device you've ever used. But there's a problem. Some calculations are so complex, so massive, that even the fastest supercomputers would need billions of years to solve them. Enter quantum computing. Instead of bits, quantum computers use qubits. And unlike regular bits, which can only be 1 or 0, qubits can be both simultaneously. This weird property is called superposition. and it's based on the strange rules of quantum physics. As you add more qubits, the number of possible states doesn't just add up, it multiplies exponentially. 2 qubits can represent 4 states at once, 3 qubits can represent 8, 10 qubits, 1024 states, 100 qubits, more states than there are atoms in the observable universe. This isn't science fiction, this is real physics, and in 2026, someone builds a quantum computer with over 10,000 qubits. To give you perspective, just a few years earlier, having 1,000 qubits was considered a major milestone. Now we're talking about 10 times that. This isn't incremental progress. This is a quantum leap, literally. But there's a catch. Qubits are incredibly fragile. The slightest interference, the tiniest vibration, the smallest temperature fluctuation, and they lose their quantum properties. The whole calculation collapses. So these machines have to operate at temperatures near absolute zero. We're talking minus 273 degrees Celsius, colder than outer space, colder than anywhere in the natural universe. The breakthrough in 2026 isn't just about raw qubit numbers, though. It's about something called logical qubits. These are error-corrected qubits that are far more stable and reliable. Instead of having individual qubits that make mistakes, you cluster many physical qubits together to form one logical qubit that can actually solve real problems. This machine has 100 logical qubits. That might not sound like much, but it's enough to start tackling problems that classical computers simply cannot solve. Drug discovery? Quantum computers can simulate molecular interactions at scales impossible for traditional computers. Climate modeling? They can run simulations with unprecedented accuracy. Cryptography? Current encryption methods that would take classical computers millennia to break could be cracked in hours. That last one has governments and corporations very interested, by the way. Materials science could be revolutionized. Imagine designing new battery chemistries, new superconductors, new materials with properties we've never seen before, all tested virtually before ever being synthesized in a lab. Financial modeling, traffic optimization, artificial intelligence training. All of these fields could see massive improvements once quantum computing reaches practical maturity. 2026. 2026 is when quantum computing transitions from being a laboratory curiosity to becoming a genuine tool for solving real-world problems. The era of quantum advantage has begun, and once it starts, there's no going back. Milestones and moments. 2026 isn't just about giant scientific leaps. It's also about human moments, cultural events, milestones that bring people together. Barcelona's Sagrada Família finally reaches completion after 144 years of construction. Antoni Gaudí started this masterpiece in 1882. He knew he wouldn't live to see it finished. He once said, "My client is not in a hurry." He meant God, but it's hard not to appreciate the patience that went into this building. Generations of architects, working from Gaudí's original designs and models, finally placed the last stone in 2026, a century after his death. A fitting tribute. The Winter Olympics come to Milan and Cortina d'Ampezzo. Italy hosts the Games for the 4th time, and for the first time ever, the Olympics have 2 host cities in their official name. Thousands of athletes, millions of spectators, a global audience watching ski jumpers soar, figure skaters glide, and hockey teams battle for gold. But the biggest sporting event of the year? That's the FIFA World Cup, and this one's historic for multiple reasons. For the first time ever, 3 countries host jointly: Canada, Mexico, and the United States. For the first time ever, 48 teams compete instead of 32. 80 matches, 3 million fans attending in person, billions watching worldwide. The final takes place at MetLife Stadium in New Jersey. And somewhere in the world, a new champion will be crowned. America celebrates its semi-quincentennial, 250 years since the Declaration of Independence, 250 years since 13 colonies declared themselves a nation. There are commemorative coins, battle reenactments, historical celebrations in Boston and Philadelphia. A time capsule gets buried, scheduled to be opened in 2276. Imagine that. People 250 years from now, opening messages from us, seeing what we thought was important to preserve. And in the world of entertainment, Grand Theft Auto 6 finally launches. It's been over a decade since GTA 5 became one of the best-selling games of all time. Fans have been waiting, speculating, begging for a sequel. And in May 2026, Rockstar Games delivers. Vice City reimagined. 2 protagonists, a map bigger than anything they've done before, buildings you can actually enter, destruction physics that put previous games to shame. Some people will spend hundreds of hours in this virtual world. And you know what? That's fine, because virtual worlds are getting sophisticated enough to be genuinely compelling. On Mars, the Curiosity rover finally goes silent. It landed in August 2012 with a planned mission duration of about 2 years. It operated for 14, far longer than anyone expected. Its plutonium generators gave it enough power to keep exploring, keep transmitting, keep discovering. But in 2026, the last signal arrives. Another machine that exceeded expectations and expanded human knowledge, now sitting silent on an alien world. A monument to human curiosity, frozen on the Martian surface. And in the darkness of space, the Bepi Colombo mission reaches Mercury. Years of travel, 9 flybys past Earth, Venus, and Mercury itself. And finally, orbital insertion, the most comprehensive study of Mercury ever conducted. 12 specific objectives to understand this strange, scorched world. These moments might seem small compared to quantum computers and synthetic genomes, but they're not. They're reminders that human achievement comes in many forms: science and culture, competition and cooperation, exploration and celebration. All of it matters. All of it makes 2026 memorable. Data everywhere. Let's talk about storage for a moment, because the amount of data humanity generates is genuinely staggering. Back in 2018, the total amount of digital data in the world, the entire datasphere, as researchers call it, was 33 zettabytes. That's 33 trillion gigabytes, an incomprehensible number already. By 2026, we've passed 200 zettabytes. In 8 years, we've increased the world's data by 6 times. And the curve isn't flattening, it's accelerating. Every photo you take, every video you stream, every sensor on every device collecting information every second. Self-driving cars generating terabytes per day. Scientific instruments producing massive datasets. Social media, cloud storage, security cameras, smart home devices. All of it adds up. And somebody has to store all that data. Hard drives haven't disappeared, despite predictions of their demise. Solid-state drives are faster, yes, but they're also more expensive per gigabyte. For archival storage, for backups, for cold storage of massive datasets, traditional spinning hard drives still make sense. In 2026, manufacturers release 50 terabyte hard drives, 50,000 gigabytes, in a single 3.5-inch drive. This uses something called heat-assisted magnetic recording, or HAMR. Tiny spots on the drive platter get heated to 450 degrees Celsius and then cooled back to room temperature in less than a nanosecond. During that brief moment when the material is hot, it becomes receptive to magnetic changes, allowing data to be packed far more densely than before. 50 terabytes is enough to store roughly 12,000 hours of HD video, or 25,000 hours of music, or millions of photos, in something the size of a deck of cards. This matters because data isn't slowing down. Machine learning requires massive training datasets. Climate models need historical weather data going back decades. Genomic research needs sequences from millions of individuals. Astronomical surveys generate petabytes from a single telescope. Storage technology has to keep pace with our data generation, and in 2026, it does. For now.